Good morning, everyone. First, let me introduce myself. I'm NICOLAI TASCA from VED, a company that includes four business units, as you can see in this slide. The main services provided, excuse me, go, come back to the previous slide. Sorry. The main services provided by the VED are engineering and production of high range of gasket, pipe and fitting production and steel recovery system, highly specialized maintenance services, and emission control services. The latter is the business unit where I work as a project manager. Today, I am here to talk to you about the impact of valves on the environment. As you all know, industrial plant valves play a critical role in environmental impact. Valves can emit two main types of emissions. The first one, and the most important, is a fugitive emission to the atmosphere caused by the aging and wear of valve components and also bad maintenance management. Leakage from valve glands is by far the most common emission. They account for more than 90% of overall valve emission. Leakage from flanged joints is also possible, but although less likely. In the slide, you can see leakage recorded using optical gas imaging camera. In the next slide, I'd like to expand on fugitive emission from valves. In the 19th, the EPA was estimated that a typical refinery can emit 600 to 700 tons per year of VOCs from leaking equipment, such as valves, connectors, pumps, assembly connection, and so on. Furthermore, EPA studies have estimated that valves and connectors account for more than 90% of fugitive emission from leaking equipment, with valves being the most significant source. Today, after more than 20 years, we still have the same results. In the table are shown our data collected from service during LDR program for Italian facilities. For example, in the first line of the table are a medium-sized refinery account for about 100 source of emission. The 70% of overall emission came from valves. This value increased to almost 80% for thermoelectric power plant and decreased to over 60% for chemical plants. On the left, the figure shows fugitive emission distribution, where, as you can see, among all equipment, valves are definitely the largest source of emission of pollutants. So look at fugitive emission impact on environment. Fugitive emission of volatile organic compound contribute to the formation of ground-level ozone. Ozone is a major component of smog and causes or aggravates respiratory disease, particularly in children. Some species of VOCs are also classified as volatile hazardous pollutants, and some known or suspected effects of exposure to those hazardous pollutants include cancer. For example, some common hazardous pollutants emitted from refinery or chemical plants are benzene, toluene, and xylene. Another impact is on the greenhouse effect. So the greenhouse gas protocol within the scope 1 indicates fugitive emission as direct GHG emissions. The last impact is on the safety. VOC are flammable, increasing the fire and explosion risk at the plant. As you are aware, the best way to reduce fugitive emission, excluding manufacturing improvements, is by leak detection and repair program implementation. When LDAR requirements were developed, EPA estimated that petroleum refinery can reduce emission up to 60%, and the same results was found for chemical facility. In Italy, we again still have the same results. The picture shows fugitive emission reduction by LDR implementation in an Italian refinery. Our data show a reduction of more than 70% of emission with more than 400 tons of VOC saved in just 3 years. Also in this case, the valves performs the worst, producing the most emissions. But with an efficient LDR program, we obviously have some benefits, such as we can increase safety for workers and operators. We can reduce product losses and reduce emission fees, and decrease exposure of a surrounding community, help facility avoid enforcement actions. An efficient LDR program includes the following points. First, you have to identify components, to tag physically each regulated equipment components with a unique ID number, and you have to institute an electronic data management system for data and records, and you have to perform periodically audits to ensure the inventory updating. So you need to choose and use a leak definition, and you ever use definition lower than what the regulation requires. The most important point is the monitoring components. First of all, choose the right device to detect the leak, and then use an electronic data logger to save time, improve accuracy, and provide audit records. After a leak is detected, you have to repair components. So develop a plan and timetable for repairing components. Make a first attempt at repair as soon as possible after a leak is detected. Monitor components to ensure a leak has been successfully repaired, and replace problem components with leakless or other technology. The last point is the record keeping, where you perform internal and third-party audits on a regular basis to ensure compliance. Leak detection is by far, as I said before, the most important point in leak detection repair program implementation. Today, we have many technology available for leak detection. We can separate them into 2 main categories. The technology that meets the EPA 21 method used for accessible source monitoring and for leak quantification, and other technology that don't meet the EPA 21 method used for non-accessible source. Within the first category, we have the flame and photoionization detector, thermal conductivity, and so on. Whereas the second category, we can find optical gas imaging and ultrasound camera, so optical technology. Okay. Regarding the VOC monitoring, according to the EPA 21 method, flame and photoionization are the main devices. A photoionization detector uses a ultraviolet light source to ionize chemicals to positive and negative ions that can be easily counted with a detector. Ionization occurs when a molecule absorbs the light energy, when molecules' ionization potential obviously is lower than light energy. The same occurs with flame ionization detector, where the ionization is carried out by a flame, an hydrogen flame. They use similar technology, but not the same technology. As I said before, FID and PID are both reported in the EPA 21 method, but our field experience showed substantially different results using those technologies. Tests carried out at the same time and on real samples and in real monitoring conditions show that FID is the best technology for VOC monitoring. Its flame ionization technology, according to our experience, is less affected by interferences. FID can detect VOC presence with a higher precision compared to PID. Let me further elaborate the reasons. Using PID, some gases like methane are not ionized because they have ionization potential higher than lamp energy. And other gases can react photochemically and form compounds that can coat the lamp surface. Those gases cause a barrier effect, giving a decreased device efficiency and sensitivity. Furthermore, humidity can introduce leakage currents and refract light, resulting in lower sensitivity of the device. As a consequence, PID can be successfully used for single chemical compounds measurement in lower concentration conditions with a higher sensitivity than FID. PID can be less effective in high concentration conditions. To sum up, PID can be adversely affected in dirt and humid application and where other non-responsive gases are present, as it happens in fugitive emission monitoring surveys. However, we must say that PID remains the best technology for some inorganic compounds like ammonia. So I'll move on in organic monitoring where both technology are not applicable. For example, for hydrogen, we can use a thermal conductivity detector where the temperature change were measured, calculated, and displayed on the device. Usually, this instrumentation is used for hydrogen because it's less sensitive than FID and it is responsive to all gases. So now let's move on. Optical gas imaging technology. Largely used for non-accessible source monitoring and for smart LED LDAR program implementation. With optical gas imaging, a leak appears like a plume, as you can see in the pictures, black or white, depending on the camera settings. In the next slide, I'll try to explain what is needed to image a leak with optical gas imaging. In order to image a leak, you need three things. The first one is that gas must have an infrared absorption peak that overlaps with the spectral windows of the camera. Usually, this windows is between 3.2 and 3.5 micron. The picture, the spectrogram in the slide shows that there are a good overlapping for many gases, many other carbons, such as methane, methanol, isoprene, xene, and so on, the gas listed. The second thing you need to image a leak is that the sufficient temperature difference must exist between the gas plume and the background. A higher delta T will lead to more visible plume in the optical gas imaging and camera display. In the picture, we can see the delta T effect as the gas moves through background at different temperature. As you can see, the plume becomes invisible at the fence where the background has a poor delta T. The last thing you need to image a leak is a sufficient concentration path length. This is the path integrated concentration length of the gas measured by the gas concentration multiplied with gas plume length. So there must be gas present in the image that is greater than the minimum detection limit of the system, of course. In the picture, you can see two leaks of the same gas at different concentration. The plume on the right is more dense as there is a higher concentration of the gas. Okay. To sum up, in this table, we can see a comparison of the two techniques, sniffing, including PID and FID, and imaging techniques. To sum up, the benefit of using gas imaging is the absence of limitation for accessibility and the lower manpower required during surveys. For example, a well-trained technician using optical gas imaging can monitor up to 2,000 components per day, compared with only 1,000 components through the sniffing method. The disadvantage of optical gas imaging, however, is that the detection limit doesn't often meet with regulatory requirements on leak detection, on leak definition. Okay. The last and youngest technology used for fugitive emission monitoring is the passive ultrasonic imaging. In this case, an ultrasound camera is composed of two things: an array of microphones sensitive to ultrasounds and optical camera. In the picture, we can see the frequency range used by the camera during the monitoring service. Within this range, there is the greatest difference between the machinery noise and the gas leak sound power, providing the best detection condition for gas leak monitoring, of course, as the gas is less affected by the machinery noise. But how does it work? First, gas leaks must emit ultrasound. These ultrasound are picked up by ultrasound camera microphones, and ultrasound waves reach each individual microphone at a different time. From these time differences, the camera algorithms software reconstruct and display the ultrasound source location, as you can see in the picture on the right. The picture shows also a leak rate of almost 50 liters per hour, but it is just an estimation, not applicable for quantification, for real leak quantification. Okay. We can see the advantage of using ultrasound imaging. The first advantage is you are able to inspect area 10 times faster than with other methods. This is the faster monitoring technology available in the market. You can perform inspection in normal operation without scaffolding. And the last advantage, is, the most important, is that the technique is not sensitive to the gas type and concentration, meaning you can find out leaks of any gas type. Okay, disadvantages of ultrasound imaging. First is gas leak must create ultrasound, so minimum pressure difference is required. Then there must be a direct path between leak and camera, meaning you cannot detect leak under insulation, and sound reflection echo can be detected by the camera. The last disadvantage is that the camera also detect flow noise, vibration, ventilation, and partial discharge interfering with leak localization. Okay, to sum up what was discussed about leak detection, the table shows a comparison between the most important technology. The sniffing instrumentation like FID and PID are cheaper than other technology. They also have the right threshold limit, lower threshold limit to ever meet with regulatory requirements on leak definition. But on the other hand, the sniffing instrumentation cannot be used for non-accessible source and require more manpower compared with optical instrumentation. Okay, thanks for your attention. For any question, please come and visit us in our stand in Pavilion B.